Okay, so we're going to go over heat problems today. And we went over this on Thursday. This is in the notes from Thursday. So like if you need to go back and check that, the formula is there. So, and for you guys at home, all of those notes should be on Classroom from Thursday on that weekly overview. Okay, so let me go ahead and present my screen. Entire screen. Share. Okay, the plan is that we're going to go over a few of these problems here and work them together from the sheet today. All right, but before we do, this is the symbol for heat, Q, right? And we said there's really no rhyme or reason for it. It's just what they gave. It's the symbol for heat. So Q means heat. Okay. And we said that you can calculate the heat of a system. So you can calculate the heat of a system if you look at three specific things. You guys remember what those three specific things are? Good. Yeah, mass, specific heat, and TF minus TI, or change in temperature. So M times CP times delta T. And I'm going to go ahead and rewrite that out. So I've got mass times the specific heat of a substance times the change in temperature. So final temperature of the system minus initial temperature, okay, would give you the heat of a system. You can calculate the heat of a system. Now, one thing I don't know that we mentioned in this class on Friday was Q values. If Q ends up being a positive number, that means that heat had to go into the system to get the temperature to change. Heat had to go into the system. So we would call that endothermic. Endothermic. So if your heat value, that screen is changing colors, isn't it? Or is it just me?
It definitely is.
Yeah, right? It's weird. Okay, well, it's Monday. So if Q is positive, it's an endothermic change, okay? That means if you get a negative Q value, it would be exothermic. It's an exothermic change. It's an exothermic reaction. You can calculate heat values for physical changes or chemical changes. This week, the plan is to look at both, okay? Physical and chemical changes, all right? So let's go ahead and take a look. We're going to look at number 1 here real quick, and then we might skip down and look at number 6. Okay, let's look at number 1 first. It says if 5 grams of copper was heated from 20 to 80 degrees Celsius, how much energy was used to heat copper? Okay, and then they tell you specific heat capacity of copper is 0.386 joules, J, per grams degrees Celsius. So the first thing I want us to do is to go through and write down all of the things that we know, right? We know that we have 5 grams of copper. Which of those variables is that? Mass, good. Okay, so we're going to go ahead and say that's going to be our M, our mass. It also tells us that the heat went from 20 to 80. All right, so that's going to be our temperature difference, but we need to make sure we specify which one is our final temperature and which one is our initial, because that's going to determine whether this is going to be a positive or a negative temperature, right? So what's our initial temperature? 20. It started at 20 degrees and it went to 80 degrees Celsius. 20 to 80. Okay, and then finally the specific heat of the system. And this will be a value per substance. Depending on what substance that you're dealing with, every substance has its own specific heat. And that's the amount of heat that it takes to raise the temperature of 1 gram of that substance by 1 degree Celsius. The specific heat of copper, it says, is 0.386 joules per grams degrees Celsius. Okay. Now at this point, what would we do with these numbers? Plug them in, right? You just plug and chug, all right? So they're asking us to calculate heat. Heat is Q. So we're going to go ahead and just start plugging in numbers. We've got our mass, which is in grams, times the specific heat, 0.386 joules per grams degrees Celsius, times our change in temperature, which is TF minus TI. So 80 minus 20 would be about 60, right? Okay, and that's degrees Celsius. Now, one thing I wanted to tell you is you don't have to put up all of those units. If you know where the numbers go, you can just put in the numbers. The reason why I put the units up there though this time is because I wanted to show you that they really do cancel out. Okay, grams will cancel out when you go to do the math here in a minute. Degrees Celsius will cancel out. So what is the unit that we're going to be left with? Yeah, joules. Very good. J, joules. All right, now at this point, what do? I know you can't hear it, but they're saying multiply. Okay, yeah, right? That's what Ashton said, I'm pretty sure, right? Okay. Yeah, you would multiply. Okay, so multiply all the way across, and I didn't do this. I'm hoping you guys did, and you got it right. Anybody do this yet? Okay, Vito, what'd you get?
I got 150.
150?
Yes.
115?
0.8.
Oh, 0.8.
I meant, yeah.
Yeah. Gotcha. Okay. Yeah. 115.8. And then what's our unit, everybody? Joules, J. Very good. Nice job. Okay, now let me ask you this while we're here. If the heat that was needed to raise this system from 20 to 80 is about 115 or 116 joules, would you consider this an endothermic or an exothermic reaction? Endothermic, why? Yeah, it needs heat to raise the temperature. And the Q is positive. Q is a positive number. So it's 115.8 joules, and it's an endothermic reaction. Heat went into the system to raise the temperature. Okay? Does that make sense? All right. So what we're going to do, I'm going to keep talking. So again, like if you know what you're doing, you just help yourself. I'm going to go ahead and skip on down to number 6. And I'm going to work number 1 and number 6. And we're going to skip to part 2 and look at a couple of those. But if you don't want to get out of order, if you're weird and OCD like that, you just, you go in order. All right, here we go. I'm going to look at number 6. Number 6 says I've got a 4.50 gram coin of copper. Man, I used copper a lot. Huh. Anyways, copper that absorbed 14 joules of heat. What was the final temperature of the copper if the initial temperature was 25 degrees Celsius? The specific heat of copper is 0.386 joules per grams degrees Celsius. All right, I'm going to go through and just start making a list of all of the numbers that I have. All right. Okay, it tells me that I've got a mass of copper of 4.5 grams. And this is copper that we're talking about. It also tells me that it absorbed 14 joules of heat. Which variable is that? Yeah, heat, Q, right? So we know that the Q is 14 joules. The heat absorbed is 14 joules of heat. Now, just based on the reading there, what would you say about this system, endo or exo? Endo, right? Because it's absorbed into the system. And then it says, what was the final temperature of copper? So I'm gonna go ahead, I'm just reading along and I'm writing down everything that I'm learning about the problem. They're asking me about the final temperature, so that's something that we don't know. I'm gonna go ahead and put a question mark. And it says the initial temperature was 25 degrees Celsius. Okay, and the specific heat of copper. So CP of copper is 0.386. All right. So again, at this point now, we're just going to start plugging in numbers. Here's our formula to calculate heat. Right? M times CP times delta T. So I'm going to start plugging numbers in. I know that I've got a mass of 4.5. Got a specific heat of 0.386. And I've got a change in temperature. Remember, delta T means TF minus TI. So TF, I don't know. So I'm going to put an X in for TF. You can put TF in. I'm just going to put an X because I don't know that. Minus my TI, which is 25, is equal to 14. All right. Now, at this point, it becomes a question of, do you remember how to do Algebra 1, right? Do we remember how to solve problems like this? And listen, if you don't, that's fine. We're going to go through and work this. But like at this point, it really does just become a math problem and you're solving to find X. Okay? The way that I would do this, the way that I would calculate this is I would multiply these two numbers first. Okay? So if you do 4.50 times 0.386, you get like 1.737 times X minus 25 is equal to 14. Now, just because I don't want to have to distribute like that 1.737, and you can do this either way. You can go ahead and distribute this number to the parentheses, what's in the parentheses. I just want to, since they're multiplied together, I'm going to go ahead and take this 1.737 and chunk it over here. Because I don't want to have to distribute it to everything in the parentheses. So I'm going to take this and just take 1.737 and divide both sides by it so I can get it over here. Does that make sense? That's what I would do. Just because I'm lazy. 14 divided by 1.737. And I got 8.06 over here. 8.06 is equal to X minus 25. Yes, Jacob.
What's with the like multiple dots on question 6?
I don't know how to use a typewriter. Is that what you guys call it? Typewriter? Yeah. Oh, it's a Chromebook, right? My finger got stuck.
So that's just supposed to be like one.
Yeah. It's supposed to be one that's fixed. Yeah, sorry. All right. At this point, what do you do? How do you solve for X? Add 25 to both sides, right? So we're going to add 25 to both sides. And so X equals 33.06. So X equals 33.06. And what is that? 33.06 what? Degrees Celsius. Very good. Degrees Celsius. So our final temperature of the system was about 33.06 degrees Celsius. You could round that even if you wanted to, since most of your other numbers are between 2 and 3 digits. You can even round it to just 33 degrees Celsius or 33.1, and that would be fine. Okay? Does that make sense? Good. All right. Okay. So any more questions about those two? All of the ones in part one are dealing with problems just like this, so where you're solving to calculate heat, okay? All right, I'm gonna go ahead and stop the video there for just a second and give you guys a minute to work on those top 5 problems, and then we'll take a look at the ones on the bottom.